Hi everyone, welcome and thanks for coming to this talk. In this talk, I'll be covering our CVPR paper, LAVENDER, Unifying Video Language Understanding as Mask Language Modeling. Our poster ID is 240 for the session on Thursday afternoon. Please come to visit if you are attending CVPR in person. In this work, we unify all tasks from pre-training to downstream as open vocabulary generation via mask language modeling. We remove task-specific heads and loss designs so that all tasks can share the same MLM head and be modeled as the same MLM objective. With this design, LAVENDER can be easily adapted to multitask fine-tuning and can enable zero-shot capabilities of QA tasks, even without leveraging the superpower from large language models. First, let's revisit the common practices in video language modeling, that is to add a task-specific head for each task or even each dataset, which usually does not have good zero-shot capabilities for QA tasks. For example, for open-ended video QA, usually a classification head of a predefined ANSI dictionaries are added to a pre-trained model. For retrieval, either classification or ranking head is added to rank over positive or negative video text pairs. You can see that different tasks or even datasets may require different head and need to be optimized with task-specific losses. This figure compares LAVENDER with existing methods. Unlike task-specific designs in existing video language methods, LAVENDER unifies all tasks as mask language model. We adopt an encoder-only architecture with a lightweight MLM head instead of the heavy decoder in unified image text modeling. Now let's look into the details of LAVENDER. We adopt the same architecture in Violet, where the text encoder is the word embedding layer, and the video encoder is video swing transformer, and the fusion encoder is 12 transformer layers for cross-model modeling. For pre-training, we adopt mask language modeling and video text matching. The main difference is that video text matching is reformatted as MLM. Specifically, we append a mask token to the text sentence to mimic the masked textual inputs in MLM. At the mask position, LAVENDER reuses the exact same MLP used for MLM to make a prediction. Although the ground truth label is restricted to 2 tokens, true or false, but the model predictions are made across all vocabularies. To adapt to downstream tasks for text-to-video retrieval, we rank the video text pairs by the probability of predicting true at the mask position. For multiple choice video QA, we concatenate each answer choice sequentially to the question with a SAP token in between. A mask token is then added at the end to allow the model to make a prediction of the correct index for the ground truth answer choice. For open-ended video QA, as the majority of the answers are only a single token, we simply append a mask token to the end to directly make answer predictions. For video captioning, we follow our previous work Swingbird to adapt a causal self-attention mask where the caption token can only attend to the existing output tokens. During training, we randomly mask some words with mask token and apply the MLM objective. During inference, the caption is generated in an autoregressive manner. At each generation step, the model sees the entire video input and previously generated tokens, plus a mask token, at which the model makes a prediction for the current token. We first compare LAVENDER with task-specific baseline, which adopts the same architecture but with different head designs and losses for different tasks, versus the same MLM head and objective in LAVENDER. Due to limited time, let's focus on the results with video language pre-training, which is the second half of the table from line 5 to line 10. Under single task fine-tuning, LAVENDER significantly outperforms task-specific baseline with plus 4.9 on meta average. Under multi-task fine-tuning, LAVENDER consistently outperforms task-specific baseline with plus 5.9 on meta-average. Additionally, Lavender can also support task-specific prompt or task-specific token for multitask fine-tuning by simply prepend the prompt or alignable token to the text input. But our results show that it doesn't bring much performance improvements. To further examine the benefit of multitask fine-tuning with our Lavender framework, we compare different multitask settings. The goal is to answer the question, can we have a unifying architecture that supports all downstream tasks simultaneously without introducing any task-specific heads? Note that the previous study was conducted on a fraction of the tasks considered here. We consider the following multitask settings. The first one is a single set of parameters for all tasks. The second is the best performing checkpoint for each task while training the all-in-one model. And the third is multitask fine-tuning as second stage pre-training and then fine-tune on each task. From the table, we can see that the best performing setting is multitask fine-tuning first and then followed by single task fine-tuning. All-in-one is also very competitive with only minus 0.5 performance drop from single task fine-tuning baseline or meta-average. And compared to task-specific baseline, we observe a consistent gain of plus 4.2 on meta-average. Lavender also showed clearly better generalizability to unseen testing data when trained with limited training data. In this figure, the red line is Lavender and the blue line is the task-specific baseline. The two dotted lines denote 90% of model performance when trained with all the training data for each model. As shown in the figure, Lavender can easily achieve 90% of the full model performance with much less training data. As mentioned, Lavender can be seamlessly applied to video QA in a zero-shot manner with the same MLM head from pre-training. Here, we compare with previous method on zero-shot video QA. Lavender can achieve competitive zero-shot performance even when pre-trained with much less data, 5.5 million versus more than 69 million, and without leveraging powerful large language models. When comparing fine-tuning results with SOTA, without any task-specific architectures, Lavender outperforms the prior SOTA on 11 out of 14 benchmarks considered. Thanks, and we hope to see you in our poster session.